So I will share a little bit of new results based on old work on looking at traffic waves, my favorite topic in traffic flow, non-equilibrium effects, humans cause inefficiencies, and the questions what can be done about it if you have some level of automation, but also then actually quantifying a little bit what this means for the energy impact of traffic flow, but also not just quantifying it, but establishing a little bit of an understanding of why certain efficiency gains can be expected based on the structure of traffic models and based on the structure of energy models. So that's a little bit my goal. It's just scratching the surface, but I hope I can highlight a little bit of these aspects. So this is based on two projects. One is a more fundamental NSF project where you saw that ring road experiment in some prior talks, and also I will show it later, and then an ongoing circles project with multiple institutions, some of which are listed on the left. And I want to make a shout out to a PhD student, undergrad student, and postdoc on the Temple team, many of which have contributed great parts to this work. So to dive right in, the motivation essentially for what I'm concerned with is that I'm saying that fully autonomous vehicles are still the far future, but vehicle automation, automated vehicles are already here. Essentially, many vehicles that you can buy right now will have adaptive cruise control systems, which means that you can actually, you still have to steer, but the velocity control essentially taken over by your vehicle. And it automatically slows down when a car is ahead, and it does the car following for you. And that, of course, is a level of automation that takes over a fundamental task that usually humans do. And of course, that affects a little bit how you drive, but it also affects then indirectly how the car behind you behaves, whether it's automated or is human controlled. And therefore, this propagates through the whole traffic stream, and you're actually modifying the dynamics of the flow, so of the whole system. I'm really interested in the system level impact. That's the main focus of my research here. So, so the question is, what will be the impact of adding a few automated vehicles to the traffic flow? And of course, people have hopes, people have expectations. Generally, when people talk about vehicle autonomy, vehicle automation, of course, the hope is that it increases safety, whatever that means. It hopes that the automated vehicles themselves will be more efficient. And then sometimes also it's pointed out that there might be a serendipitous efficiency benefit to the other vehicles because the automated vehicles drive, for example, more smoothly. So sometimes people call this speed harmonization. Now here we want to exploit a more aggressive paradigm, namely specifically say you have a few automated vehicles and you want to actively use them as traffic flow controllers. So those are actuators, and the objective is to steer the whole flow, not just your automated vehicles, but the whole flow, all the vehicles, all the humans on the road, into a more efficient flow regime. Now, if you do that, then essentially you have Lagrangian traffic flow control. And of course, that could complement existing Eulerian, so fixed in space controls like ramp metering, variable speed limits that essentially are bound to a certain infrastructure. So, so the transition that has already happened in data collection, going from stationary data collection means over to cell phones, could also happen for the sake of traffic flow control. And the focus here in this talk is specifically on the idea of, can you dissipate traffic waste and can you prevent phantom traffic jams, okay, via vehicles that are automated, a few of them, as you see at the bottom, that of course might have some information about what's happening downstream through vehicle to vehicle or vehicle to infrastructure communication. So I'll talk about first a little bit about the ideas of traffic flow control via autonomous vehicles and what's established, then spend 50 minutes about non-equilibrium traffic flow theory. So what are the mathematical foundations that can guide you? And then specifically talk about the manifestations of these controls, A, on the traffic flow, the flow perspectives, and B, on the energy perspectives, and then close with some conclusions and outlook. Now, before I move to traffic waves, let me just point out on one slide that there are also ideas that how a few automated vehicles could be used to affect the traffic flow, even if you don't talk about traffic waves. So in mathematical terms, if you just have the Leiter-Witham-Richards model, just equilibrium traffic flow dynamics, and you have at x equal to 0 a big traffic jam because you had an accident here. So this jam is going to move backwards. You see it here. Then, of course, after eventually this jam will move backward like this really far. if you didn't do anything meanwhile on removing that bottleneck. So the idea is now you have one single vehicle here, say here 40 kilometers upstream of that accident, and it knows about it. What could that vehicle do? One vehicle. Well, the idea is that vehicle could drive in the right lane slower than the rest of the flow. And if the rest of the flow is sufficiently dense, what it will actually do is serve as a moving bottleneck and therefore induce a modified traffic flow state. It will increase the density behind itself, and resulting, of course, by conservation of vehicles in a slight reduction of density ahead of it. This shock will travel forward, this shock will travel backwards. So eventually these two shocks will meet. You will get a traffic state like this. Then eventually that control vehicle, of course, will hit the highly congested region. There you turn off the controller, nothing to be done. You still have the leftover of that state, so you still see the impact until eventually, of course, you're back to where you would have ended up if you didn't have a control, but you ended up there in different means, and it can actually be shown that one can design some of these controllers in a way that you save fuel. Now, this is in this preprint here. You can look it up. I don't want to talk about any details. Just to point out that this was coupled together with some energy models. It was a case where we chose numbers representative of German highways, where you have higher highway speeds. And the main idea why you save fuel here is that you replace essentially going really fast, where you have a lot of air drag, and then super slow by some intermediate density that is more advantageous. Yeah, so you can affect with just a single vehicle things on a big picture. Of course, that comes at the price as being quite invasive. And then you need to have a vehicle that drives slower in the right lane and serves as a moving bottleneck. Some people might have societal problems with doing such controls, but it's still interesting to explore these possibilities. So this is just one slide on a known ways idea, just to highlight this. But I want to dive in particularly in stop-and-go traffic ways. So this is our experiment that we conducted a few years ago, essentially ring road, reproducing the example from the Sugiyama experiment, and many other people have reproduced this. You start out with all vehicles on a road driving normally, and then dynamically you get these stop-and-go traffic ways. And then once the arrow turns red, we turn on a controller on that vehicle that is designed with a goal to dampen the stop-and-go traffic waves. In the beginning, to dampen them, the nonlinear ways, right? It needs to leave a little bit of a bigger headway. But over time, of course, hopefully it can steer the flow into a more uniform flow regime. And you see, of course, that as we saw in the prior talk, of course, that this can be resembled and reproduced in simulation in many ways as well. So here there's a set point of a controller right now found that yields the smallest amount of velocity variation. And with a set point 7.5, we explore in this controller on a slow time scale different set points of how one could choose this average speed. The reason is that once you remove the waves, the flow actually turns out to become more efficient, as you see from the throughput numbers. And then after some time, you can turn off the velocity controller and can confirm that slowly these waves start building again up. So it's like a dynamic instability. The human driving is just slightly so unstable that it will produce these stop-and-go traffic waves, unless, of course, you can control for them. So if one compares the strong waves here in the beginning with the best controller here and compares different metrics, one sees that this kind of sparse control, one vehicle in 21 vehicles being a control vehicle, can have a lot of benefits. For example, economically, the fuel consumption turns out to be almost cut in half. And that's the real measured fuel consumption from the vehicles. 70 times less strong braking events used as a proxy for safety. You have less velocity variation, which translates into, for example, clean air benefits, and also you get efficiency gains. So the throughput turned out to increase by 14%, because of course there's no physical bottlenecks here. So the flow achieves whatever it dynamically likes to have. So in this experiment, then we extracted the trajectories very precisely, applied good quality filtering, validated filtering that gives you good acceleration trajectories, and then you can put models on top for the emissions. And you see that not only do you gain a substantial reduction in fuel, you also gain a reduction in emissions. What is particularly important is that not all behaving the same way. It turns out that greenhouse gases are less reduced, but NOx, the stuff that we often associate with clean air in cities, actually reduced by 73%. So cut down to a quarter. That's quite substantial if you think about implementing some of these ideas in urban areas and cities. There's also some interesting things that we found out anecdotally here, based on the instructions you give the drivers. In the first set of experiments, we told the people just to safely follow the vehicle in front. And then you got these blue dots here. You got these red dots here. And then we told them, okay, drive as before, but now, we got these blue dots. And then we told the people, try to close the gap. Try to close the gap whenever safety permits. And that made actually drivers more aggressive because they were focusing on gap closing. And it turned out that actually turned then the flow into giving stronger waves and also a higher fuel consumption here. So the driver mindset turned out to be actually quite important on the waves that you get. So in some sense, we push the people from relaxed West Coast driving to aggressive East Coast driving, if you like. So it really matters also, of course, what the mindset of the drivers is. Now, this was anecdotally here, but I want to highlight that when people just use an off-the-shelf traffic simulator, of course, these aspects are usually not in there. So doing experiments with real humans to inspire these things and inform these is, of course, an important future work that needs to be done here. So this was mostly based on humans and how can a single control vehicle improve the situation with humans. But like I said before, some vehicles that are out on the market that you buy have adaptive cruise control systems. So in another experiment we did a couple of years ago is we took our lead vehicle here, that's Jonathan Sprinkle's cab vehicle, and then we had 7 vehicles of an identical make to follow. And then at some point, the lead vehicle was reducing its speed from 50 miles per hour to 44 miles per hour. You see here what the lead vehicle did, and then you see how the follow vehicles react to this. Now, there's no humans in the loop here. This is fully automated. You just have humans for doing the steering and turning on and off the adaptive cruise controller. But what you see is essentially a lack of stability here again, a lack of dynamic stability. So the initial velocity drop here, you see a little bit of an undershoot and then gets to the new speed, right? But you see that the undershoot increases more and more from vehicle to vehicle until the last vehicle is knocked out of the adaptive cruise control system and then pulls over here. So imagine having a chain of 7, 8, 10 of these vehicles on a roadway, which of course does not really happen still. The market penetration rate is too low of these vehicles, but imagine that were to happen. And of course, this is not being improved via software updates, and that could be a real concern. So also stability, dynamic stability. The first vehicle looks still okay, right? It's undershooting a little bit, but when it builds up, these are really concerns one needs to have on looking at the system level performance of these systems. All right, so the questions and tasks are essentially assuming that a few automated vehicles are successful at wave dampening and suppression. Well, the first thing is the hope that we can have is that they kill the waves, and they kill the waves by essentially reverting the flow back to a uniform flow state. So if you think of that ring road, you started out with a uniform flow, then the waves started developing. So the hope is that you can undo that. So therefore, without going into details how to exactly do this, the exercise essentially becomes to understand how much worse are the waves compared to the uniform flow that you started with initially. So it doesn't actually become a control question, it becomes a question of understanding the waves. And that actually I want to stress is the key exercise that actually has to be done first. Then the second question is, how well can a design controllers get close to this optimal controller, the theoretical optimal controller? So the question is, how bad are these traffic waves with regards to A, flow property, and second, energy consumptions here. To get started on understanding this, let me present a little bit on theory here. So I'll go a little quicker on here because I've covered this in other talks. You can look at online recordings, but in a nutshell, I focus on 2 ways to describe traffic flow. One is microscopic, through individual vehicles, and one is macroscopic through partial differential equation models, as you see on the right here. So the key distinction in both of these cases is their first order dynamics, where essentially you say the speed is some given function of your gap to the vehicle ahead. And there's second order dynamics, where you say your acceleration, Newton's laws of motion, is some function of your gap to the vehicle ahead, your velocity difference to the vehicle ahead, and your own speed. In this case, simple car following dynamics, so you're only affected by what the vehicle directly ahead of you does in your lane. Can, of course, be made more complicated, not a conceptual problem, but it's good to study these simple systems fundamentally. On the other hand, you have macroscopic models where you have a traffic density that is a function of position on the road and time, and it evolves to partial differential equations. Here, in this case, a first-order hyperbolic system, the Leiter-Witham-Richards model, the LWR model, or here a second-order model, the R-Russell-Jang model, the ARZ model, that are suitable adaptations of fluid dynamics and gas dynamics to give you the evolution of the macroscopic quantities of traffic density and traffic flow rate that one cares about. Now, the key point is that first-order dynamics can represent essentially equilibrium dynamics, including shockwaves, traffic jams, red-green light dynamics, but dynamic instabilities, phantom traffic jams, and so on are not produced by first-order dynamics. You need second-order dynamics or some other effect, like first-order with delay, which I'm not focusing on here. But in these instantaneous in time state-space models, you need second-order dynamics to produce these effects. So in microscopic car-following models, essentially, of course, for example, on a circle, could be a long road as well. So you have vehicles at positions. I'm using the convention here that the vehicle J follows the vehicle J plus 1. So they are ordered as you go downstream along the road. And the second order model dynamics essentially just is that the vehicle acceleration is some nonlinear function f of the gap s to the vehicle ahead. So front bumper minus front bumper of the two vehicles minus the vehicle length. For simplicity, I'm assuming all vehicles have the same length here and are identical. So the nonlinear function of the gap, the rate of change of the gap, which is the velocity difference, and then your own velocity. Then you assume further that this model is so that you have a uniform flow in which all the vehicles are equispaced and go at the same speed, and then you linearize around this uniform flow. Standard exercise, you find that you get a linear cascade system where the coefficients alpha 1 to alpha 3 are the partial derivatives of that nonlinear function with regards to its arguments evaluated at equilibrium. Then you see that, okay, the jth vehicle is just affected by what the j plus first vehicle does. That, of course, cascades through your chain, your beats of vehicles on the chain. And then you see that if you look in frequency space, so do a Laplace transform ansatz, then you essentially get that the jth vehicle behavior is given by the j plus first vehicle behavior via transfer function, which for these models looks like this. Doesn't matter so much. You can look at the Bode plot, standard engineering approaches, and understand when do you have stability. Well, you have stability if this transfer function is so that it never produces a vehicle to have a higher amplitude of perturbation than the vehicle ahead, meaning that along the imaginary axis, purely oscillatory modes, the modulus of this transfer function is always less or equal than 1, which then one can calculate for this particular function translates to this simple to check algebraic condition. And of course, the idea is that humans, based on what we saw before, slightly violate this condition. So this number would be slightly negative for a certain regime of density states that one cares about, right? Where traffic is still flowing, but is quite dense. And then in this unstable regime, you get that small perturbations that constantly happen, or here infinitesimal, but small perturbations, result in exponential growth of some wave numbers, and until, of course, the nonlinearities kick in. And then, of course, this linearization doesn't cover the behavior. Then you get other effects. For example, you could get vehicle collisions in some bad models. You could get nonlinear traveling waves in some well-designed models. So, and then also, of course, if one just looks at preventing traffic waves, so keeping the uniform flow stable, of course, one can immediately study these systems from the point of view, what if I add a few automated vehicles? So what if I have a few vehicles follow a different function with a different induced transfer function, G here, that has parameters beta 1, beta 2, beta 3 that are different, but has the same equilibrium solution. So leaves the same spacing when you have no waves. Then one can do the same kind of analysis and get a similar stability criterion, gamma being the penetration rate of your control vehicles. You need that the transfer function f to the power 1 minus gamma times g to the power gamma needs to be less or equal than 1 for all frequencies omega that you might encounter. And you can also do some analysis on this here, right? So think of a ring road, 100 vehicles, you have like 10 control vehicles. An interesting fact that follows from this analysis here is that you would get that the stability properties of the system are independent of the relative placement of your control vehicles. So you would get the same stability behavior whether you place them equispaced, every 10th vehicle is a control vehicle, versus all of the 10 in one cluster, and then the rest is uncontrolled. That was one thing that bothered us for a while, because that cannot be true in reality, right? That you can take like 1,000 vehicles and not have any control vehicles nearby and you still stabilize it. So one thing that was found also, and we understood this then, is that, of course, having a system that is stable, in this case, asymptotic stability, doesn't mean that the system remains close to equilibrium. That's a really interesting consequence here that we noticed for the following reason. If you think of the system constantly being exposed to noise, so written as a stochastic differential equation, what happens in these systems when you have just one single control vehicle and then a long chain of slightly unstable vehicles is you have a single kick to one vehicle, and then that kick goes upstream in the vehicles, amplifies, always a little bit until it wraps around. There's a ring road, then the red control vehicle dampens it, right? So as t goes to infinity, this one kick decays. So the system is asymptotically stable. All the eigenvalues on the left have plane. But at transient times, you get actually a transient growth that could be very big. And it's the bigger, the more vehicles you have behind each other without a control vehicle in the way. So therefore, while the system is asymptotically stable, it does not mean it remains close to equilibrium if you have small, non-infinitesimal, but actually small perturbations, because you get that exponential growth. So there's a lot of interesting structure also in understanding these microscopic models. And then, of course, one can look at microscopic car following models, for example, the intelligent driver model, optimal velocity model, follow the leader model. Without going into detail, you can pick one of these models, calibrate it either rigorously or in the I-norm to reproduce quantitatively some of the flow behavior that you observe in experiments, as it's done at the bottom, including the fact that you want at that equilibrium flow on that ring road, you want the flow to be unstable. In both scenarios, they're identical left and right. You have that all vehicles are human controlled, but the blue vehicle on the right will be turned over to a smart velocity controller at t equal to 120. But before that, you see that traffic wave that has arisen. And now the goal is, once the vehicle is turned on the right, so look at the bottom right, now it's turned on the velocity controller. The goal is now that it now follows a different law, but only that one vehicle. The rest of the cars remain in their unstable state. But this vehicle succeed in keeping the flow at bay, right, and bring it closer to equilibrium modulo little noise that is constantly added to the perturbation. And there's also, you see, the blue vehicle has gone further now, so it has resulted also in an efficiency gain in the flow rate. So these results that were shown in the beginning experimentally can be reproduced via models. In this case, microscopic models. Now I want to highlight also macroscopic models. Why does one care about macroscopic models? Well, a few reasons. They describe the variables that are oftentimes measured, namely flow rate, densities, bulk, throughput of roads, box speeds, directly. They don't track individual vehicles, so they are scalable to really like large urban systems in potentially real-time setting, but you're choosing big cells when discretizing these models. In a cell transmission framework, they provide nice frameworks to input sparse data. So there's and also privacy aspects and other aspects where you don't want to track individual vehicles. So there's a real role for these macroscopic models in transportation engineering. And one point is that one can also reproduce these phenomena, in particular instabilities and traffic waves, in these macroscopic descriptions. For example, here, one possible form, the Payne-Witham model here, but it's the same for the All-Russell-Zhang model for the experts in the room on these models. So you have a hyperbolic part, and then you have a relaxation term here. So the speed of a vehicle relaxes in time towards the desired speed function, capital U. Now, if you have these kind of models in the structure, they have two speeds of information propagation here, which are the eigenvalues of the hyperbolic part Jacobian matrix. Those are the two speeds of information propagation, one traveling backwards on the road, one traveling forward on the road. Now, with these systems, one can look at the formal limit, tau, this relaxation timescale going to zero, so cars relaxing faster and faster. Then formally, of course, little u would converge to capital U because you relax faster and faster. And then the system would, in fact, reduce when you substitute it into the top equation to the LWR model, the first order model. And then one can do theory and actually show, and in fact, Witham showed this already in the 1950s, that the stability of a uniform flow is equivalent to the second order system reducing to the first order equation, converging in some sense to the simplified dynamics of the reduced equation. And that is all equivalent to a simple to check condition, which is called the subcharacteristic condition, which means that the characteristic speed of the LWR model the derivative of the flux function, the slope in the fundamental diagram, is in between the two characteristic speeds of the 2x2 system. And if and only if that condition is satisfied, you get the stability of uniform flow. If it's violated, then you get traffic waves. You get traffic waves, and these traffic waves can now be found by making essentially a traveling wave ansatz. So taking the equation, the system, and saying, I want to look only at solutions that are just dependent on a single variable that's a traveling wave. So x minus st, where st is the unknown traveling wave speed. You substitute in the first equation, you get a relationship between rho and s using one factor of integration, which is m, the mass flux of vehicles through the wave. Then you take this, make the same ansatz in the momentum equation, the second equation, use substitutions, and you reduce your 2x2 system of PDEs to a single ODE, scalar ODE. That is your Jammerton system. There's a little bit of detonation theory that needs to be applied to find the relationships between M and S. I'm not going to go into any details here. The main point is one can almost semi-analytically construct these traveling waves and then compare it to a simulation and see that, okay, I see how the true solution behaves. That's the blue curve. Here we are numerical simulation, but it's more or less converged, so it's more or less the true solution. You get this dynamic instabilities, but I can also predict a priori what this traveling wave will be as t goes to infinity, and it will essentially be this detonation wave, this orange curve. And you see at the bottom a realization, a visualization of what this means to the individual vehicles, right? So what comes out on the right comes in on the left. But the simulation here, the model is carried out in a macroscopic sense. So one can reproduce the same kind of behavior via partial differential equation models as well. Now, one important fact is how this all manifests in the fundamental diagram. So the fundamental diagram of traffic flow is really one of the key ingredients in traffic flow theory and traffic flow engineering. Essentially, you plot the flow rate of vehicles as a function of the density. This can be, of course, found via data. You get some data points here from sensors, then they spread out here, and then they go down here again. So then people oftentimes draw a curve like this here, a function. That is your functional relationship of flow rate versus density. That is equilibrium flow. So if flow had no instabilities, it would always lie on that curve or close to that curve. But now in reality, of course, you have these instabilities. And one can then show that whenever you have waves, nonlinear traveling waves, what actually turns out that each of these waves is a segment that forms a straight line in a fundamental diagram. This again can be seen by starting from the continuity equation, which just means conservation of vehicles. And if you have a traveling wave, then the consequence of this is that the flow rate is just m plus s rho. So it's an affine linear function of the density, where the abscissa is the mass flux of vehicles through that wave, and s is the traveling wave speed of that wave. So here you will have some waves that travel forward on the road. Here you will have some waves that travel backwards on the road in this model. And you get that this set valued part of the fundamental diagram is being produced organically through these models just by essentially stop and go traffic waves. Of course, in reality, other aspects contribute also to a spread in a fundamental diagram, like heterogeneities of cars, but this is the manifestations of these waves. And then, of course, this is the point-wise evaluations along these waves. If you now average your total effective density and your total effective flow rate over the wave, the big wave, the total wave, then you get that the set of all the averages would form a set below the fundamental diagram. So whenever you have a wave state, you are generally below the fundamental diagram, meaning for the same average density, you actually get a lower throughput, a reduced throughput. And all of this can be explained and constructed via this traffic flow theory, the non-equilibrium traffic flow theory. So with that established, we now should look at how this manifests. So the first thing is, what are the manifestations of traffic waves onto the flow? Here's again a simulation of the intelligent driver model. It's a long road here, 8-kilometer road, 300 vehicles placed on it, initially uniform, and then the model chosen in a way that for this average density, it's a ring road again, but really long. So these waves have space to breathe, right? So they can do whatever they dynamically would do. So it's a simple way to still have a ring road where you have a control on the density, but make it really long so that you see what the vehicles, you don't constrain the waves to being having the periodicity of the ring, right? So before you saw a 250 meter experiment of a road or 300 meter, here this is more than 8 kilometers. So 300 vehicles placed and chosen so that for this average density, the flow is dynamically unstable. Then you add a little bit of persistent noise to the model, and you see that slowly in time, these waves develop, and then you get these strong traveling waves that go backwards along the road, and the vehicles run through them, and in between here, they even come to a full stop in this intelligent driver model. In other ones, they might just get very slow, but essentially you get these strong velocity variations here. Now, this is the vehicle trajectories, and you can plot them, looks neat and so on, but what does it mean in a fundamental diagram? So one way to reconstruct densities and flow rates from these vehicle trajectories is essentially using kernel density estimation techniques. So you can define a Gaussian kernel whose width is chosen that it is wider than the typical spacing of the vehicles, but still localized enough that you get localized information about density and flow rate. And then you reconstruct via standard techniques that the density is just the superposition of these Gaussian kernels, and the flow rate is the same thing weighted with the speed of the vehicles. This reconstruction is nice. This is not the only way to reconstruct macroscopic quantities, densities, and flow rate from vehicle trajectories, but it is a nice way because it results in this function rho and q satisfying exactly the continuity equation that we had before. And we know that whenever you have a continuity equation and you have a traveling wave, this forms a straight line in the fundamental diagram. And exactly by the simulation, you see that, yes, if you plot all the possible points point-wise that you get from density and flow rate resulting from this traffic model, they lie in fact on a straight line. Yeah, pretty far. So you have complete stoppage out here, and you have cars going rather fast in between. Yeah, and then they go around here, brake, accelerate, back and forth, and then you see that the average flow rate and the average density over that geometron now here is a point here. Now, this is the equilibrium point that we started from. The red dot is here at initial time, or short times, right, before the waves have established. And once the waves have established, this point has moved down. It moved down vertically. Why? Because you have a ring road. And a ring road, of course, controls your average density. So your average density has to be exactly the same. But the flow rate has dropped. And it has dropped quite substantially if you look here, right? So that is what you also see in some experiments or when people show controllers that get gains in this. Now, again, this is a ring road. So there's no physical bottlenecks. So what will happen in the fundamental diagram when you get waves as you move down? Now, this actually, we looked out and said, okay, well, but real roads are not ring roads, right? So what are the scenarios that can happen? Where does the point move in the fundamental diagram from the original equilibrium state down to when you have the waves? And we came up that essentially three key scenarios. One is, and here you see the simulation, start with vehicle positions here, just the dots here, and then the vertical position is the speed. That's one way to visualize these waves. So here you have fast speeds where the vehicles are far apart, and then here they're stopped in between. So this is an unstable regime of the intelligent driver model here. And then, as we saw before, when you have the humans only, you start out in the fundamental diagram and develop instabilities, you move down here. And then the idea is, of course, if you now had an AV-based control, a few control vehicles that can drive it back and dampen these waves, ideally the best possible controller, the optimal controller you could design without telling you how it looks like, would move you back up here. Yeah, and a suboptimal controller would lie somewhere in between here. Yeah, so you get this nice regime. Now that's for a ring road. Another regime is you have one lead vehicle that drives at a fixed constant speed, so a leader of the pack. Yeah, nobody can overtake. If you drive in an HOV lane, that's not an unusual situation. Yeah, then you have vehicles behind, and you see that after some time, the lead vehicle drives at a constant speed. The vehicles behind are relatively uniform still, as we saw also in the experiment before, right? When you had the ring road, the vehicles behind had very little oscillations, but as you go further back, you get more and more stronger oscillations. Now, in this case, the speed is fixed. So any vehicle behind, even in the presence of waves, on average has to drive with the same speed of the lead vehicle, because if not, it would either fall behind or eventually hit vehicles ahead. So it has to go with the same speed. Now, the speed of the fundamental diagram is the line that goes through the origin. So here you can also show that, in fact, theory predicts you have to lie on that line. Yeah, and you see that, in fact, the simulation confirms this. You move down here along this line, and then the optimal AV controller would bring you back up. Sorry. And the third regime that we focus on is you have a stretch of road, you have an outflow, or a bottleneck somewhere, a physical bottleneck that limits your throughput fundamentally. So flow cannot exceed, that goes out, not exceed this vertical line here, the flow. And then you see that you see these waves here, but essentially what happens is in the presence of waves is that you move sideways here, still under the fundamental diagram. And then if you have AV controllers, you could push yourself back up here, right? So you get fewer cars on the road segment when you have these waves. They spread their elbows essentially when they have these waves. So this establishes a lot of fundamental understanding on how these things look like and behave. And of course, that is understanding that has to be considered with these waves and when designing controllers. Now, I want to leave it here to just give you a glimpse a little bit on what one has to consider when looking at the flow manifestations. The last aspect I want to highlight is energy manifestations. So this is an ongoing project where we look at energy models, the energy consumption, fuel consumption for combustion vehicles, battery depletion for electric vehicles, hybrids. It's really complicated. In particular, it does not just depend on the instantaneous fuel consumption rate of a combustion engine, does not just depend on what the vehicle is currently doing in terms of driving behavior, it depends on a lot of other things. But dominantly, it's affected by essentially instantaneous speed and acceleration. So essentially, we're working on some pipeline that produces these models where the instantaneous fuel consumption rate here for, in this case, this is in collaboration with Toyota. So we have the Tacoma vehicle, Toyota Tacoma, as a nice traditional fuel consumption vehicle. And then Prius EV, it's called here. It's an idealized vehicle of, if the Prius were a fully electric vehicle of the same mass, what would be essentially the energy metrics here based on how quickly does it deplete the battery. So what's the equivalent power consumption in kilowatt equivalent in both cases that is being used. Now, you see here that you see these non-convexity effects and even discontinuities here in this contour plot. This is due to gear shifting, especially up here in the high acceleration regime. There's downshifting needed to sustain these speeds. So what we say is, yeah, that's very vehicle specific. We want to sort of capture the key quantitative behavior of these models, but average out the gear shifting effects and other aspects and produce simplified models with the idea that it represents still this being typical vehicles, but we don't want to design energy metrics that are very specifically exploiting the gear shifting set points of these vehicles, because in reality, of course, we don't want to assume that the whole traffic flow is Tacoma vehicles, but is similar types of vehicles. So therefore, the rationale is to produce very nice and models here that whose contours look like this. So this is work in progress for other types of models, but here it's for these kind of models. Tacoma as a representative of a combustion engine, Prius EV as a representative of an electric vehicles. So these are also quantitatively meaningful in an average sense. And then one can take these intelligent driver models and look at what happens when you put energy evaluations, point-wise, of course, but then averaged over the whole simulation out and compared in particular with regards to what if you had a uniform flow, which we test by taking the same model with the same fundamental diagram, but changing the parameters in a smart way so that the dynamics become stable, but otherwise everything the same, so that you actually just simulate uniform flow behavior. And then you compare it with a simulation where you get these waves and then study the fuel consumption and energy metrics, energy demand for the electric vehicle in the strong waves regime, and you essentially compare these two. And then you look at the percent decrease in energy consumption that arise as a function of the background density that you encounter whenever you have waves here. And you see that the following function. For the Tacoma, you get this blue curve. So you get here a percent decrease energy consumption here of up to 75%. This is really, really significant, really tremendous. And I want to put a warning here. These high efficiency gains are, first of all, the theoretical maximum that could ever occur if you have the best possible controller. And second, the waves in this parameter regime of this intelligent driver model, which is a standard parameter regime that people use, but I want to say a warning, these are really strong waves. These are really extreme waves. So just a little bit of warning, if you use these models, especially off the shelf, to take this with a grain of salt. Ongoing work in our team to, of course, get better calibrated models. But for now, this is an existing off-the-shelf model, slightly fine-tuned from our side. It still gives a good guideline. So you see that these are the energy efficiency gains from a Tacoma, the combustion engine. They're above the energy gains you get from the electric vehicles here, at least in this density regime. That is to be expected, because if you structurally look at how these functions look like, the combustion engine and the power demand, the energy consumption is always non-negative. Yeah. Here in the strong braking regime, it's zero, but you essentially convert kinetic energy into heat, right? So you're wasting energy. Whereas you have a certain level of regenerative braking within limits here, right? There are limitations to regenerative braking, but some regenerative braking in the electric vehicles. Now that, of course, makes a huge difference. And of course, when you think of stop-and-go traffic waves, it means you're not driving along the A equal to 0 curve here, but instead you're going constantly accelerate, brake, and of course, regenerative braking makes a huge difference, which is why the energy gains by wave dampening are less for an electric vehicle than a combustion engine vehicle in this medium density regime. One really interesting aspect that we found is that if you look at the really high densities, it actually is the other way around. And that again bothered us for a while, because you still have regenerative braking versus no regenerative braking. And there's a lot of interesting aspects if you look at the potential energy gains, depending on what type of vehicles you have. And in short, the explanation here is that the combustion engines have an optimal driving speed here that's a minimum. If you drive slower, you actually consume more fuel per distance traveled, so you become more inefficient again, whereas the electric vehicles become more and more efficient the slower you drive. And that is the manifestation here of these different aspects. So the energy gains you can get also with regards to how the rest of the flow is composed are quite interesting and non-trivial. All right, now leaving it here just as a glimpse again, let me finalize this with the conclusion. So first, vehicle automation is happening, not fully autonomous vehicles, but automation, adaptive cruise control. And we, of course, need to understand the pitfalls and the opportunities that arise from the resulting heterogeneous system dynamics. Humans still dominate the flow on the road. So one is far away right now from these AV-only solutions like platooning and other things that are, of course, being explored. But right now, it's just a few of them. So the idea is, can one explore already right now Lagrangian traffic flow control? So few control vehicles make the flow more efficient. And one thing that's nice here is there might be a free lunch here, because these automated vehicles will be on the road anyways. So why not deploy them for a greater good? Now, you saw here some information on the optimal efficiency gains that could be achievable with perfect controllers. And they're quite good. They're good looking, right? Whenever you could cut the energy demand of unsteady traffic in half, potentially. Yeah, so they're quite promising. And you can get flow efficiency gains. Yeah, pump more cars through the road, which also, of course, would have some real interesting benefits. I want to close with pointing out that the key challenge in designing controllers that do that, it's not so much designing controllers that smooth the flow. That actually turns out to be not so hard if you know roughly what you're doing. The real part is to design controllers that do that in a socially acceptable way, both to the driver or the operator of the vehicle who decides to turn on, for example, flow smoothing or optimal velocity control, as to the drivers behind who might get really annoyed by somebody leaving huge gaps for the purpose of flow smoothing. So that is actually, as I see it, the key open question that still needs to be addressed in future work. Thank you very much.